It's your birthday too. So many birthdays.
What'd you get?
Not mine.
Oh.
These 3140 maybe.
Oh, an XPL maybe, yeah. Cool. Morning, folks. How'd lab go last night? Making progress? So people got some simulation running. Some people have simulation running. Anybody got any Verilog integrators running? Anybody? Got it? Good, excellent. All right, good. So if you decide to just start by simulating one integrator, if you start by simulating one integrator, you have to give it a couple of inputs. One, you must give it an initial condition, obviously, and you have to give it a VN. So let's say that if you were to set the initial condition to 0 and VN to, let's say, 0.001, then you would expect to get what out? What happens when you integrate a constant? You get X. You get time out, right? So you'd expect this to increase, get to some maximum 1 or 1.99, and then it wraps to minus 1.99. Boink. So what you're going to see is something that looks like this. If you were to say, I'm going to simplify things and set the input to 1, what are you going to see? It's going to be almost incomprehensible fast square wave. It's going to be +1, -1, +1, -1, +1, -1. You're going to say, that's not a ramp. So it's working correctly, but because of the finite range of the fixed point system, it's overflowing essentially on every time step, or every 2 time steps. So if you're going to test an integral this way, give it a small input and a 0 initial condition. If instead of having an input be a constant, you feed it back, of course you should get an exponential. But then you better start with something other than 0, because otherwise it'll be 0 forever. So what questions came up in lab last night? What's working? What's not working? What do you want to hear about?
I think one issue that we had that took us a while to figure out was that the main differential equation in the lab, they suggested you should use x1 and x2, but it turned out that we should actually be using like the wall minus x1.
Well, that's what the Matlab code does.
Right. Yeah.
And that's why I put the Matlab code in there. Yeah, so when you're actually coding this, as it said in the debug sequence, this is the Matlab code you should refer to. And let's see if I can remember how to open that now. So in this Matlab code, it does in fact use differences between the x position, and in this notation, x1 is a position, x2 is a velocity, x3 is a position, and x4 is a velocity. So I'm subtracting off the left wall there because it was easier for me to keep track of the arithmetic that way by subtracting off the hard bounds. But this is exactly the force equations that you want to use. Now, the one thing that makes this easier is that the way the lab is written, only spring 1 has a nonlinear cubic term. Therefore, you can set 2, 3, and whatever the middle one is called to 0, or just not put those terms in.
So on that term, since we're using 2.16 for all our fixed points, the cubic term can overflow that?
Nope, can't.
But since we're doing x1 minus, or x1 plus 1, because we position the left wall at -1.
Ah.
Past x1 equals like 0.25.
So,
0.25 cubes.
so you're saying that if this spring is far enough from the wall,
Yeah. The wall's -1.
the wall's -1, but 0 is in the center, right?
So it has to go past 0. It's
It has to go significantly past 0.
whatever the cube root of 2 is, I guess.
What is the cube root of 2? I don't happen to carry that around in my brain. 1.2 something, right? Because it's 1.4 is the square root, 1.414.
So that goes past point like 2 or point 3.
I think it's 1.3 something. So, yes, that will do it. So don't do that.
So you just assume that's not
No, you don't assume it. You make sure it doesn't happen.
by the initial conditions.
Yes, by the initial conditions and by simulating the very set of constants you're going to use in your Verilog in Matlab. And it better work in Matlab, and it better not go outside the bounds at any time. So how would you make this more flexible? You could have give a bigger fixed point range, of course. You could use floating point. One group 2 years ago built a custom floating point, 18-bit significand, 8-bit exponent. It was in stripped down IEEE format, and because it was in stripped down IEEE format, they could use the weirdest trick for getting a square root. Does anybody know this? There's a graphics trick. Some graphics guy figured out a way of doing a fast square root for numbers that are in IEEE floating point format. You take the whole 32 bits, you right shift it. What the hell does that mean? You right shift the exponent into the significand, and then you XOR or you AND it with a constant, and you get the square root within 1/100%. You look up computer graphics fast floating fixed point, floating point square root, and so their goal was to produce a gravity simulation. So they needed to calculate an inverse square law. In fact, they needed the inverse 3/2 power of the distance between the gravitating objects, and so they needed to take a 1 over square root, and this algorithm does it extraordinarily fast. You may find that using floating point, limited precision floating point, is more efficient for many operations, including square root. And as it transpires, some forms of digital signal processing, infinite impulse response filters that have been factored into second order sections. Are you familiar with this idea of factoring into second order sections for stability? I'll do that later sometime. But if you have factored filters, they are very much more numerically stable, but it requires wide range of number capability, which is well done in floating point and poorly done in fixed point. Anything else on the Matlab code? Any other questions on the test sequence here? So everybody's simulating now, right? Everybody's got simulation running. You better. Time's wasting. There's only 2 weeks left. Next step is get hard-coded Verilog to work. No bus master. No nothing. Just get it running in Verilog. And preferably to VGA output. Although if you were to, out of idle curiosity, if you wanted to look at the waveforms on the oscilloscope, you could code the state machine to use my audio bus master to output the sine waves to the stereo plug and look at them on the oscilloscope instead of on the VGA screen. That may be a diversion, but it could be useful. That's only if you scale time so that the waveforms are audio range. So, questions. Again, more questions on Lab 2. Questions on bus masters. So what I said I would do today is to talk about pthreads a little bit and then go back and talk more about bus masters. So pthreads is a standard package. It includes the ability to define a thread, to schedule a thread using the Linux scheduler, and to use mutex and condition variables. I find condition variables hard to use because it's hard to initialize them correctly, or at least I haven't figured out how. So I like to use semaphores, and the example I'm going to use uses a POSIX defined semaphore, which is not part of pthreads. And the first code I wanted to show you is a simple code that has 3 threads. It has a thread that waits for human input. It has a thread that prints out what you just put in. And also a counter that's counting just as fast as it can possibly count. And the output thread outputs that also. When you say counts as fast as it can possibly count, it has to be interlocked with the print routine so that you get valid numbers when you print, and you're not interfering with, there's no conflict between the print thread and the count thread, so it has to be semaphore locked. So the print thread is going to wait for is going to be semaphore locked to the input thread and won't execute until the input thread has a valid value. And the input thread is going to be locked and won't execute until the print thread is done printing your last response. Whenever you have 2 threads which are both touching the UART, they must be protected from each other by semaphore, because there's only one physical UART. And if they both try and print at the same time, you get garbage. You get an intermixed stream of characters. So the print and the read and the write, the human read and write routines are protected against each other by semaphores, and the counting array is protected by a mutex. So in the code you need to include, it's much nicer having this big, thank you so much, Wilfer. Will was tall enough to zoom the projector up 25%. So everything looks bigger. It looks bigly, in fact. So it's in the dictionary. PTHREADS and semaphores gives you the libraries necessary for this. We're then going to have some input buffer, which has to be protected. We're going to have a couple of mutex, one for the input buffer, a buffer lock, and another mutex pthread. It's of type pthread mutex T. It's going to be the count lock. So this is going to be the mutex that protects the counter variable against corruption. Then we're going to define two semaphores. One called the enter condition and the other the print condition. So when this is signaled, the human can enter something, and when print is signaled, the print thread prints something. And there's a couple of counters defined. So, sorry for the lousy formatting. The tabs are handled weirdly by the web server. So there's going to be a void function which is a thread and will be defined as a thread in main. And it's going to immediately drop into a loop. The thread's going to immediately drop into a loop that waits for the print condition. When the print semaphore is signaled, the scheduler will wake up this thread, ask the human to enter a string. Oh, it locks the buffer. It locks the buffer so that no other process, like the print process, can corrupt it. It grabs the input buffer through scanf. It unlocks the print buffer. Then it posts, which means signal. It does a semaphore signal to the enter condition. So now we go to the right thread. It does a wait on enter condition. It locks the buffer. It locks the count. So it locks the buffer memory. It locks the count memory. It zeros the count. It prints the count, zeros the count, unlocks the count, unlocks the buffer, and signals that the print is complete. And then the counter just sits here and counts as fast as it possibly can. There's no wait, there's no nothing. You lock the count, you increment it, you unlock it. If you get rid of the mutices, that's the plural of mutex? Mutexes? If you get rid of the mutexes, this thing increments at about between 200 and 400 million per second. That's about the CPU speed for a while loop. Yeah, the CPU is running at 900 megahertz, so 2 to 400 million a second makes sense. When you start protecting with a mutex, then the rate drops to 9 to 10 million a second because of the overhead in the scheduler to mess with the protection. If you don't protect it, you get the most bizarre results when the other thread zeros the counter or doesn't quite zero the counter, or zeros one byte of the counter before you get a task swap, or does something, you know, just it's completely random what happens. Interestingly, if you make 2 instances of this thread and run them both on the same and run them both on our system, it slows down. And the reason it slows down is that the scheduler says, oh my God, this fool is running processor 1 at 100%, processor 2 is completely kicked back doing nothing. I'm going to migrate one of the processes onto processor 2. It does that for you automatically. You have it running on both processors. Now the mutex has to be an interprocessor communication, and it slows way down. If you instantiate this twice and use a pthreads attribute to force both processes onto the same processor, it speeds back up to 9 million a second. So main is very straightforward. You declare structures for each of the threads of pthread underscore t. You initialize the semaphore. The read is not ready because nothing has been input, but the print is ready because anything can be printed, and one of them better be ready to execute. If you initialize them both to 0, the system is deadlocked by design. Neither of them will ever execute because neither of them can ever be signaled. So we have to set up one of the initializations with a signal. We're also going to set up an attribute for pthreads that says that the processes, the threads that we're generating are joinable. That means if you specify a join point, that the program cannot progress beyond the join point until all of the threads have joined. So it's a blocking point that says, I'm not going any further until everybody quits, until all the threads exit. So we're setting up the join state, create the 2 threads. You associate a structure with a pointer, and you can pass some attributes to it if you want, and you can pass some parameters, and there's an attribute here that I didn't use. Then, if we put a pthread join here, all we really need is one of them here. The system will never exit because my threads are all in while ones. The threads never exit. Therefore, they can never do the join here, and main never exits. So that's the basic structure of a threaded system. There's a few other little quirks, but really the system is rather straightforward. You create threads, you lock them with semaphores or a mutex, and they share memory. So there's automatic communication, shared memory communication between threads. The good thing is that's fast. The bad thing is you have to protect it with a mutex, because otherwise the shared memory will get clobbered. Any questions on this? It's really straightforward. It just worked out of the box, yeah.
There was a second argument on the semaphore initialized. It was like there was the pointer and then a 0 and then the count. Do you know what that is?
On the semaphore init.
So that's second to 0.
Oh dear, what is it? I don't remember.
Okay.
You'll have to go. I mean, this is all in on man pages. It's all standard C, and I just have to go look it up, which I don't want to do right at the moment. The second example here sets the affinity to force the two counting threads onto the same processor. The next example is a much longer example because the two threads handle two pieces of an audio generation system. Thread 1 opens a UDP port to the PC so that Matlab can spew a wave file. Yes?
So the second argument is whether or not it's shared between threads of a process or between processes.
Ah, and this is shared between threads but not between processes. Thank you. That makes sense, right? And so the process is private, but you could make it global. Thank you. So so the first thread here opens up a UDP communication, grabs audio, and stores it in an array. The second thread takes that array, takes data from the array, and puts it through Qsys to the bus structure to the audio codec and plays it. So the first process is filling an array from Matlab running on the PC. By the way, Matlab is really slow at producing packets. Frighteningly slow. But it's fast enough for an audio channel. And then the second thread is taking the same array and filling the audio FIFOs whenever there's enough data in the array and enough space in the FIFO. So the first process, the first thread is just straight up high-level Linux, networking stuff, and the second thread has all the FPGA dependencies for address space and locking when the FIFO is full, making sure that there's at least 6 slots available for audio, because it turned out to get enough throughput, Matlab had to send rather long packets. The packet overhead was high, so sending 6 or 8 samples in a single packet was much better than sending 1 sample. So I was sending 6 at a time, or 8 at a time, I forget which. And so when you barf those into the FIFO, you have to make sure there's enough space in the FIFO. Now, mixed up with all of this is you've got this long array that's being dynamically filled and emptied by these two threads. You better lock that array when you're doing the array operations, when you're doing the array write on the UDP side and the array read on the FPGA side. So I figured once I managed to make this thing work, I had some idea how everything was going to hang together. There's a bunch of includes here. We're including IPC and interprocess communication and the socket library and a bunch of IP conversion stuff and who knows what else. And as usual, with all of this, Stack Overflow is your friend. So I generate a gigantic buffer here and a couple of mutices, or just one actually, really. It's a shared buffer lock. And we need all of the addresses to the FPGA that are in the address.h file. So this is where we're going to, these are the variables that are going to be defined during mmap operations. The first thread then is just read UDP. Oh, that came from Linux howtos.org. Very useful site. And you do a bunch of magic, and you open the socket. You set up the structure for how you are going to connect to the server. You give it some port number. I chose 9090 for no particularly good reason. It was easy to type. And then we bind the everything together. And at that point, we can do a receive from. We can do a receive from the socket and load up an array. I used a start character as an S, and if the first character is an S and the system is not started, then and the share oh yes, and we aren't at the end of the buffer, then we just do a scanf on UDP buffer and decode. It looks like, oh boy, is this crude? 1, 2, 3, 4, 5, 6, 7, 8. 8 samples. Drop them into the array. I should say we put them in temporary storage, drop them into an array, increment the shared buffer by 8, and then leave. And the audio FIFO sits here and grabs stuff out of the buffer, and then has to do a hardware-specific FIFO lookup to see if the 24th through the 31st bit of this specific address is greater than 6. 6? I thought I got 8. Oh, maybe this is a mistake. Maybe I didn't update it. Oh, no. That's right. I was sampling on the Matlab site at 8 kilohertz, and I needed to play back at 48 kilohertz, so I just duplicated each sample 6 times. 6 times 8 is 48. So this then says, for every one sample we have at the input, we're going to put 6 copies into the FIFO. It actually sounds pretty good. A much better approximation would be to do a linear interpolation across the samples, but I didn't bother. And the key here is that while we're doing the operations on the buffer, we're locking the buffer. And I don't want to talk about all the details, but we are locking it until we're done reading so that the receiving process doesn't corrupt the buffer while we are reading it. I was pretty happy when this finally played music.
Bruce?
Yeah.
Back on the read, the UDP read thread.
Mm-hmm.
How come you increment the buffer after you unlocked?
Oh. You're saying increment this by 8 after I unlocked it. You know, that's probably a mistake.
Okay.
I probably should have done that while it was still locked, yes. So now let's go back and talk more about bus masters. You're probably going to want to thread orient some stuff. My guess is that for Lab 2, you are not going to need to thread anything really, because all you're going to do is have a user interface that's waiting for a human command. And then that human command is going to be sent out over the bus, and then you're going to wait for another human command. And the bus send is so fast it doesn't make any difference to the human. So for Lab 3, which is drum synthesis, I mean, there's an open design question, and that is, what is the performance of the HPS relative to the FPGA fabric for large parallel operations, the things that can run in largely parallel on the FPGA? It may be that you get an optimal solution by running part of the process on the HPS and part on the FPGA fabric, in which case you're going to want to have a thread which is separate from the user input that runs that, thread. There also may be, the best way to do this is to run a thread on each processor that computes half of the drum, for instance. And then you probably would want to, that means you'd have 2 threads running with high speed of communication across a boundary between them. But I really don't know. I really don't know what's optimal on this FPGA in terms of number of nodes. Yeah, Will.
On the P, so you have the P thread where you set the attributes, so that way the OS wouldn't schedule one of the threads on the processor. Is
Yeah.
there an attribute that can say, hey, I'd like you to try to schedule this on?
Yes, you can force one thread onto one processor and another thread onto another processor. The default is load balance. The scheduler will try and load balance the 2 CPUs. Or if one saturates, at least it'll migrate a thread over to the other processor. But you can bind a thread to a processor.
Okay.
How will those communicate through your caches, or is it just through main memory?
Well, you can't tell the difference between cache and main memory. If threads share memory, even if they're on different processors.
Okay.
Furthermore, threads that are on different processors all have access to the same FPGA memory buses.
Okay.
Because all of that goes through the L3 cache communicator. I don't have a good feel for what happens if both processors are pounding on the FPGA bus at the same time, trying to do high-speed reads and writes. I suspect that you should mutex lock those. If you have a multiple cycle read, for instance, let's say you have to read an X coordinate, a Y coordinate, and a color, then and the other thread is reading an X coordinate, a different X coordinate, a Y coordinate, and color. You could imagine that the bus transactions would get mixed up unless you do some sort of mutex protection between the 2 threads. So I talked about VGA bus masters a couple of times. Do we want to do that again at this point or not? Is it too soon? to do it again.
You talked a little bit about wiring up hardware interrupts.
I can tell you all I know in about 2 sentences. I haven't tried it yet on this architecture. There is certainly an interrupt line, and the HPS will recognize an interrupt, but you have to modify the kernel to make that work. And in the interests of trying to get the course running, I didn't have time to blow the system away and start over a couple of times. So there are directions in the I believe it's getting started with DE1 SOC, very near the end of the manual, that talks about how you set up an interrupt handler in Linux. You don't actually have to recompile the kernel, but you do have to insert a routine into the kernel. I haven't tried it. And I can show you where the documentation is, but that's all I know about it. You got to really want to do it.
But has it gotten easier with the popularity of the Raspberry Pi? It seems like something a lot of people are going to want to do.
Somebody who's taking Joe's course could probably answer that better than I can. It's my impression that the Raspberry Pi out of the box does not do interrupts very well. Is that true?
Well, just like software sort of interrupts, like the product library you can use.
Right, there's some sort of Python library or C library that does an interrupt-like thing like the Arduino would do. You attach an interrupt and it does something which is kind of interrupt-like, but it's not a hardware interrupt. So the latency is rather long and variable. I don't know of anything here that would do that. My inclination is to say that if you need really fast response for something, put it in hardware rather than put it on the HPS. What I'm trying to do right now, in between meetings with students over writing seminar, is to modify the Qsys layout for the audio or video system so that the VGA controller is driven only by SDRAM, which is at address C000000, and uses no on-chip memory. Got that working. The next step is to use the video in, map the video in to on-chip memory. And that's necessary to do because the clock that runs the video is not generated by the FPGA and is therefore asynchronous. And the on-chip memory is two-ported, and you want to be able to drive the clock off of the video input. And you also want to be able to simultaneously read this thing onto the bus. So the on-chip memory will do the video in. The VGA will be connected to SDRAM. What I want to do now, the next step is to write a bus master. I haven't done this yet. Write a bus master. Write a bus master that reads reads the on-chip memory and maps it to an arbitrary place in SDRAM so I can have a window that moves around the screen with the video input. I think I know how all the pieces go together, but I haven't actually done it, so until I've actually done it, I don't know. But I think I know, which means I'm hallucinating. So, but the alternative to that, if you don't write a busmaster here runs at about 50 million transactions a second on the bus. If you don't do that, then you have to read the on-chip memory using the HPS, take it over into an array in the HPS, and then send it back across the bus to the SDRAM for display. And that's going to be guaranteed not to do more than 2.5 million pixels a second round trip, which is just barely fast enough. It's fast enough by a few percent to do video. But it's going to take the whole bus bandwidth to do that. That's ridiculous. So what I'd really like is a busmaster that takes commands from the HPS for X and Y position. You've got the VGA screen here. You take an X and Y and you map the video input into that location so that you have hardware window control. That would be cool. Now, the next thing is to figure out how to mask it so the HPS can't draw over that to make a true window out of it. I haven't figured out how to do that yet. Like all the systems on this FPGA, there's multiple ways of doing things. We could do it in hardware on this side. We could do it in software and copy across the bus. And there's probably various hybrids of this that will be the final solution. Just haven't figured it out yet. So the next step after the simulation is get the full numerical integration system with all 4 integrators running in hardware. So get it running in hardware, get some sort of output you can look at. If all else fails, I suppose you could slow the solution rate down to 1 hertz and PWM blink 2 LEDs. So that you could watch the LED intensities change with the position of the 2 masses. Might be entertaining. But probably the better thing to do is as soon as you get the simulation running, output it to the VGA, because that intellectual property, that IP is already there, it works, it just takes an address and a color. What do you want to hear about next? Well, we'll work our way through Lab 2, and then sometime next week start on Lab 3, get the warm-up going for Lab 3. There's a lot of setup for Lab 3 because I have to warm up your brains on the wave equation again, and then on finite difference approximations to the wave equation, and limits of stability of a solution, the Courant condition. Ooh. Anybody remember the difference between a Neumann and was it a Neumann and a boundary condition? What's the other one? Anyways, got to go through all that stuff and warm up your brains again on differential equations, partial differential equations. Then we have to start talking about how to parallelize that, because you're going to be graded on the number of nodes you can solve at audio rate. Bigger solutions make more accurate drums. Now there's an interesting problem with that. Very big drums have very low frequency. And if it gets below audio, it's really hard to test because you can't hear it. But there are various solutions to that. One is to make the drum asymmetric, make it a strip-like, so that it has a fast mode this way and a slow mode this way. Then it sounds like you're banging on a steel plate. We'll work on that, start on that sometime next week. See some of you in lab this afternoon. Oh yes, there was one last thing. I postulated that I could be in lab on Wednesday afternoon, starting from 1:30 to 4:30 next week, if anybody cared. Does anybody want me to sit in there for 2 or 3 hours and answer questions and go over stuff? Would that be useful? I'll be happy to do it. Okay, so there's a couple of people that would like to see that. So I'll plan on being in there on Wednesday afternoon. If nobody shows up, I'll leave. But I'll be there.